It's a pleasure to be here. In this talk, I will present the work related to the characterization of complexity in abstract art using topological invariants. It's evident that art screams complexity. This is precisely what we observe in the field of physics, which motivates me to determine correlations between these two areas, science and art. This. No. Okay. Before delving into the work related to art, I would like to present what I understand by complexity in physics and what nature itself shows us as complexity. The image of blue patterns showcases structures in 2 dimensions of turbulent effects using the Ginzburg-Landau equation. And the image I've chosen in this case is a pattern of a purple cabbage. In such examples, nature shows us that complexity appears in different systems. The main motivation of studying and measuring complexity in our areas arise from studying nature, understanding mathematically the structural properties, not only in physics, but also in biology and social science. Describing complex patterns, understanding where they come from, and using techniques or tools that, as physics, we are more or less accustomed to use. A fractal dimension, I believe, is one of the most commonly used measures. And the basic idea is to understand the patterns that emerge in nature, define their geometry, spatial, and temporal behavior, and in that way, better understand the dynamics of complex systems. For example, in the work, it's called Hermidal-Cocho, they analyze how the patterns change according to pigmentation in the snakes. They found that there are interactions that produce not only points but also lines, polygons, horizontal lines, triangles. It's fascinating. In this slide, I show some coral patterns. These images are from the National Ocean Services of the United States. The shapes, the structures in which the complex inherent process organize themselves to generate these behaviors that appears is, well, these forms are incredible. There are many examples in nature and obviously in physics as well. However, one of the first works I studied, was the patterns from a Mexican muralist, David Alfaro Siqueiros. Siqueiros was a Mexican muralist who developed new techniques to paint, but also started the first dripping process in a workshop organized by Siqueiros in 1936. Pollock was one of the participants, and perhaps in that workshop, he experimented for the first time with the dripping technique. When I learned about Siqueiros' work, it was through the interest of the Professor Cetina, who is an art restorer, and wanted to understand if the patterns of the work could be analyzed from physics. We found that was possible. Okay. In this work, in that work, titled The Beard of Phantoms, Siqueiros experimented with some initial paint dripping techniques, played with the canvas movement, and achieved many complex systems. Okay, in the task of investigating how these patterns arise, it was found that the density and viscosity of the paint, in addition to the painting technique, give rise to these fascinating structures. That's where my interest in analyzing patterns in art begins. The way in which the cicados, I'm sorry, I'm back. The way in which the cicados patterns were studied consists of pouring white paint over a layer of black paint, and due to density effects, the patterns emerge. This is now the Rayleigh-Taylor stability. When studying complex systems, complex patterns, and system dynamics, the interest areas is in finding correlations between art and nature. For example, on the right side, the patterns achieved with a reaction known as Belousov-Sabotinsky is shown as an example of a non-equilibrium thermodynamic states resulting from the chemical oscillation of bromide and an acid. However, when one becomes familiar with the work developed, the artist, Mr. Doddle, one can evidently and quite optimistically found a certain resemblance in terms of the structural distribution of the strokes, thinking that the boundaries of the reaction could be considered strokes in some direct comparison. Well, the main objective is to establish correlation between physics and art, and if possible, provide a mathematical description of complexity. Not all patterns are complex. Some are the results of regularities, repeating small patterns generated by sequences, or making a small change in geometry. In this sense, we decided to study carefully complexity in abstract art. However, it doesn't mean that regular patterns don't have complexity. From the point of view of geometry or topology, patterns with an apparently ordered distribution have certain degree of complexity, not only because of the curve or straight lines, or the interaction between them, but also because of the dynamics that control the creative process. But what does complexity mean in abstract art? Well, complexity in art means many things. The definition depends on the artist, the technique, the creative process, style preference, etc. But as a physics, we have to choose a measurable criteria and choose works of art that are mathematically complex. One of the first decisions we faced was selecting artworks. When delving into the artwork, the decision-making process is complex. Sometimes a piece catches our eye, even if it's not a complex piece. However, the appreciation of art is a relevant factor. For example, this piece by Jade, for which I did not receive explicit authorization to use its image, despite requesting it, exhibit great beauty. It's full of shapes, colors, textures. I'm not an expert but in grad art, but these kind of works are beautiful. They create a nice sensation. That's exhibit what happened when we choose the artworks. There are many works of art that we like, but they are not necessarily complex or do not have features of complexity. And there are also others that we don't like, but they serve our research purpose. So we wanted to measure complexity, the color, the brightness, the distribution of shapes, the outline of objects, etc. all play a role in deciding which work we would analyze. This piece by Julie Meriton, for which I received kind authorization, is magnificent. It represents a new complexity. It features multiple strokes with few colors and textures. It's a work that invites understanding of the creative process. Like hers, here is a list of artists who created incredible works. All of them somehow fit into abstract expressionism. And perhaps one of the future projects I will undertake is focused on studying artists with the gender variable, comparing the complexity of female talent and understanding from that perspective the nature of art creation. The work I presenting to you is about topological invariants used to quantify complexity in abstract art. The fundamental idea is to measure complexity using very numbers from various artists framed within abstract expressionism and compare that degree of complexity with the king of abstraction, Jackson Pollock. Jackson Pollock has been studied extensively. His work are striking. The study of his technique, materials, and the psychological, artistic description of his talent has been a subject of many studies from different perspectives. He has had an artistic influence not only in expressionism, but also in the study of complexity. I have decided nearly 10 years to analyze his work. We have studied his technique, the materials he uses, the type of strokes. We built a robot to draw paint by controlling the speed, height, and viscosity of the painting process. Many children have participated in workshops we conducted, and we have motivated them to paint like Pollock. This material has been studied, quantified, classified, using fractal dimension. And I believe that one of the most well-known impacts was the work, of Richard Taylor, when he published the first study on the subject in Nature. Professor Taylor truly had an outstanding impact in inviting us to study art from a mathematical point of view. The drip or pouring technique is one of the teachings that stand out the most, and we have conducted many experiments regarding it. His work are easily recognizable. There is no doubt that it's Apollo. One of the first tasks one undertakes is measuring the fractal dimension. All the scale considerations, counting methods, exponent approximation, scale laws, dimensions, spectra, etc., were considered. These are two examples of Jackson Pollock. They are so beautiful. Well, it's a Pollock. These are some preliminary studies. In this work, we analyze multifractal dimension in 22 Pollocks. We calculate the spectra of dimensions and describe the space of complexity. We found multifractal characteristics, the fractal evolution by year, but also the evolution of complexity. We found a correlation between density and fractality, and we recognize the necessity to measure complexity using a different methodology. One of the simplest exercise is measuring fractality in the drawings from workshops with children to see if any achieve similar magnitudes. And no, no one have come close to the values reported by Pollock. The conclusion is that it's clearly possible to quantify and classify Pollock's complexity using fractal dimension as a measure to identify an artistic work, and also conclude that Pollock was unique. Well, Pollock fractality lives between 1.8 and 1.89. The lowest points are from large works, Summertime and number 10. They are long works or large works that have some repetition of patterns. And when we measure fractality, the scale is important. We divided the image into several sections and we measured the fractality. We found that depending on the area, the value of the fractal dimension changed. For example, if we take into account a large image, the fractal dimension has a low value. But if we take a small area, the fractal dimension has a value close to 2. Here we recognize the correlation between density and fractality, but also that complexity cannot be characterized with only one measure. What about with the technique? If density determines fractality, then can anyone paint like Pollock? Well, no. Okay. Given the background of Pollock's study, we took on the task of selecting works from different abstract expressionists. Lee Krasner, Marcel Barbeau, Brice Marden, Jean-Paul Riopelle were some of the selected artists, with some of their works meeting our selection criteria. What was this criteria? Image that had few colors, well-defined and dark lines or strokes, and a clear background. In the case of Pollock's works, they were also chosen using the same criteria, which was challenging. In his brief period from 1946 to 1951, well, although mural is an impressive work, we did not select it due to the presence of outlines or shapes, perhaps in another study with different objectives. We choose works by Brian Gisin, Lee Krasner. Here I show use the works that are coherent with the criteria and allow for as a focus study. These works, this one, yes. These works are by Philip Custom and Arthur Pinajian. You can see we looked for works with a few colors and the strokes are clearly visible. These are by Brice Marden and Marcel Barbeau, where even though multiple colors appears in the later, the black strokes are visible. When I was working on the selection, I wrote to Marcel Barbeau, asking for a permission to use his image. He said that he was interested in astronomy and listening frequently to radio and television programs about research, about natural phenomena. So he mentioned that discovered photos of a solar storm, and he painted some works inspired on that. Well, it's nature the universal musa of abstract paints? Probably yes. The methodology we use involves transforming the high-resolution image of the artwork into a binary image. The algorithm used has been tested by many image analyses, and the grayscale binarization threshold and selection of the area normalized according to the size of the artwork. All are well established and defined. Then, with the binarized image, it's possible to quantify the very numbers using the CHUM software. They are calculated. Well, as the previous talks, in general talk, very numbers are topological invariants that allows quantify the connectivity between continuous spaces and the spatial distribution of the spaces or holes delimited by connected regions. Beta 0 measures the number of connected regions in a space, and beta 1 the number of holes delimited by those regions. For example, the image shows a small region of one of the analyzed artworks, this one. The binarized image is shown in A. In B, the connected regions are illustrated in green, and in C, some spaces or holes are painted in red. In other words, the very numbers, beta 0, tell us how many connections exist in an image, and beta 1 tell us the number of spaces or holes in that same region. So, how do we know that our methodology works? So, we create synthetic abstract art. We generate image with an algorithm in MATLAB and placing lines simultaneous strokes of different thickness and lengths randomly distributed over a fixed space. The image shows some examples of the lines placed varying in width and length, and as more lines are added, the space fills up. In this image, we calculate the very numbers, and it's evident that if the number of strokes or lines increase, the number of connections also increase. If the lines are width, the space fills up faster than if they are thin. And as more lines are added, the number of intersections between them grows. Hence, the number of spaces between lines will also increase. The figure shows the behavior of beta 0 and beta 1. The field symbols represent the behavior of beta 0, and the empty symbols represents beta 1, changing the width of the lines. Can be observed how they grow until a limit and then decrease, indicating either total connections or all the spaces being filled. The correlation between density and a measure of complexity is confirmed again. There is a dependence on the density of points and the measure of complexity. In this case, it is with very numbers, and confirms what is already known in the box counting method in fractal dimension. We have to consider that by adding lines, the space will be full and the connectivity will tend to 1, because all the lines are connected in a single path. This is the reason why the behavior of both very numbers decrease. Connectivity grows as does the number of holes, but then all the space is filled. In the case of Pollock, it was found that there is a correlation between both varying numbers. Coincidentally, during the years of greatest development of his ripping technique, there is a higher degree of complexity. However, there is also a correspondence, we will say a balance, between the number of connected strokes and the number of empty spaces. Let me show up. Okay. When comparing the behavior of the Betti numbers between Pollock's and the works of other abstract expressionists, it is identified that Pollock shows a certain clustering of results. We can see that in this figure. Indicating a correspondence of complexity between connectivity and holes. In the graph on the left, we can see that Pollock has a well-defined slope, unlike the other works. To the left, right, okay. And in this graph, we see this cloud of results that seems to always indicate a correlation line. Well, we see the triangles, the black triangles, in comparison with the empty symbols.
So these are the same Pollock paintings on the left and right?
Yes, of course. Yes, we have the same.
Different plots.
Yes, this is beta 0 and this is beta 1. Beta 0 measure the connectivity and beta 1 measure the holes. And yes, we identify the slope in the case of Pollock's. And in the case of the other abstract artists, we have different slopes. So this is a measure or a feature that indicates that complex on Pollock is higher than the other abstract expressionists.
Have you ordered the ones? Are the ones they're just ordered in terms of the ordinates?
Yes, of course.
Okay, and then those aren't. So you've done the ordering
It's
with
the same
respect to
order.
that.
Exactly. It's the
And
same
then
order.
you've transferred the ordering
Exactly.
across. So you could have done it the other way around as
Yes.
well. You could have ordered those or they'd be random.
See, exactly.
Okay, and now I understand. Sorry.
Yes.
Sorry, which paintings were they? The expressionist ones? I missed.
They're just a collection somehow.
No. The idea is the selection was to see a few colors, define strokes, light background, and we selected with so many pictures, many paintings, many.
But just you chose 30 from
the same
Mark
abstract
Rothko.
expressionism.
Like Mark Rothko, is he in there?
Yes.
No,
No,
Mark Rothko is in here.
Rothko is not. No.
Why?
Let me tell you why. Mark Rothko just have some paint areas. He doesn't have strokes.
Yes.
Yes.
Most assuredly.
Yes, but they are so, how can I say it?
Yes, so you just said, I don't like these won't fit, so we'll
No,
take
no,
them.
no, it's not like a,
Why
I
did
like
they
it, I
not-
like
why
it,
did
I
they not
like it.
include
No. The criteria was, the criteria was, we want to see, let me this kind of paintings. O sea, the idea, I can compare Rothko with Jackson Pollock because many of the works of Rothko doesn't have this kind of strikes. So this is the reason. Maybe in another study, maybe in a comparison with different purpose, yes, I will select Rothko. But in that case, we just select paintings. Looks like that.
So lines is
Look.
important. The line.
Exactly.
Are you looking for lines?
Look. Well, I love Rothko. Yes. But I couldn't select that. Okay. Okay, I was here. This is the point. Does it matter that we are comparing only Pollock's works with different artists? given that they have different styles and compositions? Perhaps the answer is yes. When considering different artists, each may have different features that lead to this scattering result. However, we are making a comparison with a uniform selection criteria with equal measurement scales and factors such as style, composition, and subjective artist features are not taken into account. Perhaps a specific study will be needed to have certainty in each case. However, the comparative works were chosen based on strokes, on not individual styles. Well, finally, when compared with a normalized value of the very numbers, we see that there are several points, pollocks, represented by the black triangles that fall within a range of higher complexity, unlike the other works. There is a correspondence between connectivity and empty spaces, which tell us that the object has a high degree of complexity. In this case, the number of Pollock's cases is greater than the others. However, a more detailed study works by the same artist or with artificial intelligence. So what is the opposite of complexity? To better understand the behavior of very numbers in works that appears to have low complexity, we conduct an analysis of Yayoi Kusama's work. In this case, we create synthetic abstract art with dots. And we repeat the exercise of creating images and analyzing them using the same methodology. Well, Kusama's work is well known. Her art is based on using dots, distributed in an order governed by artistic compositions. I won't show you one of her works because she didn't authorize it, but it's very easy to see on the internet. So we found a direct correlation of fractal dimension with the density of dots. We observed that by changing the diameter of the dots, we found an evolution behavior of the fractal dimension as the study area filled with dots until reach a maximum, at which point, when the space is filled, the fractal dimension is close to 1. I'm sorry, this is the graph. This is the graph. We can see the fractal evolution of the Kusama's paintings. And we can see that reach a maximum value of close to 2 when the space is filled up. So the idea is measure or compare the synthetic abstract art created with dots and prove the methodology used with the Kusama's painting, and we calculate the fractal dimension and the very numbers. And obviously, we obtain a low complexity compared with the Pollock's results. When we calculate the very numbers, we observe that connectivity behaves linearly with the dots, number of dots, and the maximum is reached quickly if the dots are large. Obviously, if we have a big dot, the area is going to fill up faster than if we have a tiny dot. The behavior of Petit 1 is also linear, and if the dots are small, the number of holes is higher compared to larger dot diameters. Well, the complexity of Pollock compared to the Kusama is very high and different. Kusama is example of low complexity compared to Pollock, and however, we would like to know how Pollock's complexity compares to the new abstract art. The technique has evolved. There are new artists, new expressive forms, new images to analyze, and we would like to know how that comparison looks now. Well, and also, now I am interested in working with live artists. I consider that dialogue between both parts is important. The idea is to know what they think, their techniques, the creative details, knowing deep not only the mathematical complexity, but also the artistic complexity. So I have 12 minutes. So my future work includes conducting experiments, ripping experiments, analyzing the correlation of complexity with abstract art created using intelligence, artificial intelligence, or machine learning, studying in detail the dynamics of Ciceiros patterns, and predicting complex systems and patterns based on physical condition of viscosity and density, and obviously analyze more artistic techniques. Well, I'm very grateful to my collaborators in this work, Professor Robert Zenit, currently at Brown University, and Professor Malina Lee Wong from the National University of Mexico. And thank you very much for your kind attention.
Thank you very much. We have time for questions.
When I practice the lecture, it was fine. When I hear, that's okay. Thank you. I apologize for my English.
It was okay.
So your studies raise a lot of questions in my mind anyway.
Yes, of course.
But
This is the idea.
let me mention maybe one. You have a measurement. However you do this, you didn't describe it, but of the fractal dimension for a painting by Jackson Pollock.
Yes.
Where you have a fragment and bigger fragment and bigger fragment,
Yes.
and you obtain different fractal dimensions.
Yes.
So first, let's just say that if something is a real fractal, then it will, any fragment of it should have the same fractal
Yes.
dimension as any other fragment.
Yes, this is the same idea
More-
that I have.
Yeah, more importantly, Pollock adhered to an artistic strategy that's called
Here.
all-over painting, by which he meant that he avoided creating centers of attention, and he worked to achieve certain uniformity. So I think whatever measurements you did, if fractal dimension increases with the size, I think it's a warning sign, something not quite right. It shouldn't really be like this. And my second comment, if I may, is there any reason to expect that the ratio of the first to the second Betti number is a significant indicator of complexity?
Okay. Yes. Yes. When I began to study Pollock, there was incredible topic because Pollock was unique. Maybe you know the story about Terry's found. It's a woman who discovered a Pollock in a road, and she wanted to be she asked to recognize the works, and there are many studies made to the paint. Studies found. You can find a film. There is a film. There is found.
I've seen it.
Yes. Okay. And when I saw that, I thought, maybe it's easy to make a Pollock. It's easy to falsificate a Pollock. It's not easy. So I began to study all Pollocks, all possible Pollocks that come to me. And when I identified that fractal dimension, multifractal characteristics of polyps. I studied this behavior of large image. And you measure the fractal dimension in an image. Obviously, you expect that you obtain the same dimension depending on the scale, because the self-similarity and self-affinity in many complex systems, they have to be present in the analysis. When I found this, I say depend on the scale of observation. So what does it mean? It means that there is a correlation between fractality and density. There is, I just said no. Okay, we have to prove that. We have to prove that. So the idea, if there is no correlation between density and fractality, what happened with the evolution of the fractality in image created with dots and lines? So we can control the density in the image. We have an area filled with dots and lines, and we also see that if you increase the dots or lines or field space, obviously you are going to converge to a dimension of 1 in a two-dimensional space. This is not my result. This is a result from, I don't know, in many books you can find. So maybe I'm not.
Well, actually, this is kind of a common question, not just for this talk, but for the talk of today, like that dealt with all this complexity measure. And my comment is that, I mean, I don't want to don't take it harshly, but I think that what I'm seeing is a description of a complex system without all the richness that the complex system implies. So a complex system is something for which you have emergent phenomena. And I don't see here any ways that you can talk about this emergent phenomena via this kind of measurements.
I know.
And I think that the emergent phenomena is what brings the value, the quality value in terms of the aesthetics, in terms of the message, in terms of the artistic conception.
Yes, I know.
And so I was wondering if you guys have any comment on this.
I agree with that. This is because I want to work with live artists. So the emergence of patterns, the complex behavior as a result of emerge process or interactions, for example. I don't know how Pollocks make the paintings. I just have a static pictures, and I try to measure some characteristics, mathematical characteristics. So if I talk about complexity, it's I don't know, maybe crude form to express the complexity inner in the Pollock's paints and the abstract expressionisms and the abstract art. So which one to be the correct way to do that? I have to contact an artist. I try to expect that he develop an artwork, and try to understand how the materials, for example, the density, viscosity, pressure, temperature of the paints can act together, and expect that the emerge of patterns emerge in that dynamics. So this is the correct way that we expect. We made it in physics. So here, I don't have this process. I don't have a Pollock painting. I don't have the interactions between the viscosity in the paints. So the idea here is just to measure in a static way the geometrical, topological characteristics according to the mathematical description, general mathematical description. Yes, I agree. Yes.
So this was partially to me also. So I can comment very shortly that I deliberately avoided to call it complexity. Maybe I used this, but this was not my point. The complexities are very different things. I think reduce complexity. I'm a physicist, so for me what was important is to correlate this particular features of paintings with a real experiment. Okay, and this experiment was how do people look at that. Okay, so that's why I even insisted that we're not looking for an aesthetic measures or complexity measures or something like that, but just to try to understand whether this what we calculated has some correlation to how people look at these pictures. And this was important. So this is purely experimental view. It has nothing to do with aesthetics, nothing to do with complexity even, but with finding the features which are important when you look at the pictures.
Okay, yes.
Interesting talk. I liked it. I have a couple questions. When you say multifractality, I'm curious. What do you mean by that? Do you mean the fact that the fractal dimension was changing with the
Yes.
size of the image?
Yes, different slopes.
Okay.
Different slopes. When you, I use the spectrum multifractal. It's a very common program, and you see one slope and then another.
Okay.
This
But
is
it's
what
the
I call
variation.
multifractal.
The variation in DF,
Yes,
right? Not the moments of the.
exactly.
Okay.
This is different.
Yeah, and
And the scale is important in this case.
right. Yeah. And do you have a list of? We should talk for reasons which will soon become apparent. But I'd like to see your. I'd be really interested in reading the papers that you do, especially on Elsa and compared to Pollock as well. So I think that's great. Anyway, I enjoyed that. Thank you.
Can I say, I loved the brain coral. I mean, I would have questions about Betty numbers of brain coral, but I'll just park that. It was actually, I wanted to actually disagree with Andre. I don't see why the fractal dimension has to be the same as you move along. If I take Jackson Pollock number 9 and Jackson Pollock number 10, and I glue them together, this one's got a 1.6, so that's got a 1.8, and as I gradually move along, I think it's going to change.
But this is not the case here, of course. But you have to decide, is this painting, are you going to consider this painting to be fractal or not? And remember, it's a single, and remember,
Yeah, but the 4 painters, you get a different number for each of the 4 slices.
Yes. No, but remember, his method of painting was to avoid variations from place to place.
I'm absolutely
all over painting.
Absolutely not talking about Pollock or Painter. I'm just talking about the mathematics. I can envisage a Cantor set that's got bias towards one end and different at the other end. So, and if you then move along it, you're going to get a different number. It's just a Cantor set, a biased Cantor set.
I must say that I do not understand what does it mean that the fractal dimension depends on the resolution, because fractal dimension is something which is connected with the fact that you change the resolution.
Correct.
Okay.
Exactly.
So yes. So this is the okay.
That's
What
exactly
if
right.
it's not uniform? Like, as you're saying, there's a patch. It's like a manifold instead of like just one patch. I don't know what happens in the patching sections or something, right? But you could have, if you take analytically, well, you can glue something with one fractal dimension to another piece, but yeah, within this particular scale, it's a fractal with this dimension. Within this particular region, it's a fractal with another. And but I mean, it's
People
not
say yes, people say no.
Look, did you do the following experiment? Start cutting from the other end,
Yes. Yes, I do.
and you
I did
obtain
it.
the same curve.
Yes, I did it.
Yeah, this shows that you are incorrect.
I did it.
No,
No,
it doesn't prove that
Yes, it
mathematically.
does. If you start from the other end, you get the same
No,
thought.
I think your logic is wrong. I'm not wrong about the fact you can have a Cantor set that's got a bias towards one end and towards the other. You
I'm
can
not
invent a
talking about Cantor
fractal.
set.
You can have a fractal that's different
Maybe you
dimensions
could.
at different ends. That's all I'm
But-
saying.
No, but
It's a
Alan,
mathematical fact.
yes,
What's going on here is different, and I'm not even talking about that. I'm just
Well,
talking
I'm talking about
mathematical.
this.
Yeah, that's fine. Well, then don't tell me I'm wrong, because I'm not talking about this. I'm talking about the fact
well, I
that
thought we were talking
a
about
biased,
this talk.
biased cancel set. Well, you said you said you had to have a fractal dimension that was the same absolutely
In
everywhere.
a real fractal, mathematical fractal, yes.
I was questioning that. To be honest, I wasn't disputing it. I was questioning that assertion.
It's the
Okay,
definition of a
disagree.
fractal, that the same scale all the way down.
No,
Yes.
the Hausdorff
Yes, that is the
dimension.
definition.
Well, it depends on your definition. I don't know the Hausdorff dimension of the of a point set.
Yeah.
I propose to move then to the key
Yes.
room and then discuss it further there. So thank you very much.
Thank you. Thank you.